Okay, hurry up. Okay, quiet. Quiet. Okay, it's time to pay attention up here. Like I said, this is a chapter that if you think the first two are at all hard, then this one will probably seem double hard. Okay, you need to be paying attention. And if you notice, we're going to spend 2 days on this first lesson, and it's not the first lesson in the chapter. I'm doing this one intentionally early because factoring is something that's important not just to this chapter, but for everything. And we tend to not do it very well, and so it hurts us with everything that comes after. So my goal is to spend 2 days on this. We'll have a quiz which is just this. Then we'll have another quiz on October 23rd, which will be a little bit of this and the other things that we've learned. And then, of course, we'll have the test. The number one thing that you need to know in order to succeed with this, and in this class, it actually may not be that much of a problem, but I never know for sure, your multiplication tables. Do you know your multiplication tables? Can you add and subtract quickly in your head? Right? Those are what you call math facts that were supposedly mastered, like in no later than 4th grade. If they weren't, this is going to be hard. Okay, I can't make it any easier. You're expected, like when you see 63, that instantly you think 9 times 7. Right? If you don't, it's going to be hard. But just the way this subject is, right? You've got to know your multiplication tables. So a quadratic, by quadratic, what we mean is the highest power term is squared. Whether or not it's an expression, right? Or an equation, or a function. The highest power term is squared. So why don't we call it squared? Because quadratic does mean squared, just not in English. Quadrato means squared in Italian. I'm sure it's pretty close in Latin, if you're taking Latin. So it is a way they are saying squared when they say that word. Right? So the things that we learned to do already, right, with an expression, we simplified, which up till now meant combine like terms. We evaluated, which meant plug in for the variable, simplify, right? And then we solved equations and graphed functions, right? Those are the things we've done so far. What we're going to do this time, and don't worry, the slide stays the same, except for one little thing, is we learned to factor. It's not exactly simplifying. It's like rewriting the expression in a different form. And like I said, that is a pretty important skill that just is like it's embedded in so many of the other problems. You're going to get to a place where, you're expected to factor. There are some workarounds that sometimes where you can figure out another way to accomplish the same thing, but usually you're turning it into a much harder problem. That it's like a trivial factoring problem, or it could be a hard quadratic formula, or something like that. Good? Okay. Please stop me if I go too fast. See, right? What we call the standard form of a quadratic, we'll just say quadratic instead of saying expression, function, whatever. But it's this form, right? It has no parentheses. The highest power term is on the left, right? Then the next highest term, which is x to the first, and then a constant, which has no x's, right? The letters in front, what you call coefficients, right, are a, b, and c. Those are real numbers. And a does not equal 0 because if it did, it wouldn't be a quadratic. But it could be that b or c is 0 and still be a quadratic. No, I said A does not equal 0. Right? A does not equal 0. So these are examples of quadratic expressions. Okay. Now the first two, the most terms you can have in a quadratic is 3. Right? Because if the highest power term is squared, the next term could be an x to the first and then a constant, and there's no more room to have any more terms. Right? When you have 3 terms, that is called trinomial. Right? Equals 3 terms. But it doesn't have to have 3 in order to be a quadratic. Like this one here is 2, this one has 2. You know, they're missing, the x squared minus 4 is missing the x term. 3x squared minus 9x is missing the constant. But they're still quadratics because they have a squared term. What does EG stand for? For example. For example, EG. Okay. For example. Okay. So we're going to learn 5 kinds of factoring, and we'll do the first 2 today. These 3 we'll do the next day. And my other 2 classes, it took most of the class to do these 2. You're going to do one thing that they didn't do, which is commonly what happens. So we'll do this thing which I'm calling simple quadratic trinomial. I call it simple. I call it that. It's not in the book. They don't call it simple. I've never seen anybody else do that, but I call it simple quadratic trinomial because the a is 1. The leading coefficient is actually a 1. And it makes it a very easy process. The next one, greatest common factor, is commonly referred to by the initials GCF. Right? So what kind of factoring are you doing? GCF. Getting there? Curtis? Everybody? Hunter? Good. So the simple quadratic, again, if we start with the standard form here, just in place of the a, put a 1. So you don't have an a. Right? Just x squared plus bx plus c. For example, e.g., x squared plus 5x plus 6. Right? And the kind of thinking you have to do, right, in order to factor is you have to say, well, you will say to yourself, what 2 numbers, their product is 6 and their sum is 5. Right? That's what's going through your head all the time, right? The product, the result of multiplying these 2 numbers gives you the 6, but when you add the same 2 numbers, you get a 5. Can anybody guess what 2 numbers we're talking about here? 3 and 2, right? 3 and 2. So when it's a simple quadratic, that is all the thinking that goes into solving it or factoring it. So, for example, in this one on the left, we have to think to ourselves, what are the factors of 42 that add up to 13? Think of two numbers whose product is 42 and its sum is 13. 6 and 7, right? And it should, honestly, it's assumed when you get these problems that that's how quick it comes to you. If it doesn't, then you're going to have to like list all the factors, right? 42 would be 1 times 42, 2 times 21, 3 times 14, 6 times 7. So which one of those pairs of numbers, when you add it up, you get 13? And it's this one, right? 6 plus 7, 13. Okay. So once you've got those two numbers, then here's the factored form of the quadratic expression. X plus 6, x plus 7. Done. Right? This is standard form. This is factored form. Right? The reason that we do this, okay, is because after we learn how to factor, then we start solving quadratic equations. And just think of it, up till now, when you had to solve an equation, that meant isolate the variable on one side, the answer will be on the other. Right? If this were an equation, and again, I'm just saying, if this were an equation, right, there is not actually, in what we're doing today, any equations. But if I just set this equal to 0 to turn it into an equation, there's no way to isolate the x, right? It's in two different terms. Because the x's are raised to different powers, they're not like terms, so I can't combine them. So there's no way to isolate the x, right? So this, we can't solve. This, we can. And we'll learn about that, like I said, in the next section. But that's why we go from standard form to factored form, because it's going to help us to solve equations. And in the end, not just quadratics, but all the polynomials of quadratic and higher. No, it doesn't equal 0. I'm just trying to tell you why are we doing this, okay? Like I said, don't get hung up on the fact that I did the equal 0. If it bothers you, I'll erase it. Right? Ultimately, we factor because it will help us solve equations that we don't have any methods to solve at this point. Now, if you're not sure, just to confirm, you can check your work, right? Check your factoring by multiplying these two, right? Do you remember the process to multiply 2 terms times 2 terms? Mm-hmm. FOIL, right? I mean, whether you call it FOIL or not, in some way or the other, you have to multiply these 2 things times these 2 things, which is going to give you 4 things, but then you'll combine like terms. So FOIL is a way to say that, right? What does the FOIL stand for? First, outer, inner, last, right? So the first terms, the outer terms, the inner terms, the last terms. Okay, let's see how that works. So we get x squared plus 7x plus 6x plus, and I'm just going to write this just to show where all this comes from. The last is 6 times 7. I'm just going to write it like this, 7 times 6. Right? And then how is it that we combine like terms? You add the coefficients, right? So I'm going to write this like this. X squared plus 7 plus 6 in parentheses times x plus 7 times 6. Right? That's why we go through that thought process, right? What are the two numbers that when you multiply them, you get this number, and when you add them, you get this number. Right? That's the work that we do all the time. Right? And if you simplify it, right, 7 plus 6 is 13. 7 times 6 is 42. So we got back to what we started with. So this is the factored form of this. Okay. How about the next one? What are the factors of 24 that add up to 11? 8 and 3. Any arguments there? 8 and 3? Again, you can check them all out. 1 times 24, 2 times 12, 3 times 8. 4 times 6, and then you just say which 2 add up to 11? These 2. Okay. So what is the factored form of this? x plus 3, x plus 8. Okay, what if I write it like x plus 8 times x plus 3? Why is it the same thing? Mark? What property? Commutative property, right? Commutative property says the order of multiplication doesn't matter. 2 times 3 equals 3 times 2. So don't get hung up on if you wrote this, but I, showed that. It's the same thing. Okay, try that one for yourself. Sit up, work. Come on. Hey, wake up. Get out some paper and start to work. Right? What two numbers are they? 5 and 7? I mean, 35 is one of those numbers. How many pairs of factors does it have? I mean, it's either 1 times 35 or 5 times 7. So 5 times 7 should come to you like almost immediately, right? 5 times 7. And then you check it out. Okay, 5 plus 7 is 12. Got it. Right. So x plus 5, x plus 7. How much of this did you get in your Algebra 1? A lot? A fair amount? Okay. Okay, now, what's the difference between these problems and the ones we did before? The middle number is negative, right? So remember, when we said the factors of 35, actually, it's not just 5 times 7. It could have been negative 5 times negative 7. If they were both negative, the product would still be positive. But if they were both negative, when you added them up, you would get a negative. So when you see this pattern, right, the last number is positive and the middle number is negative, that means they're both negative. They have to be, right? So again, what are the factors of 30 that add up to 11? 5 times 6, right? So we could, don't do that. 1 times 30, 2 times 15, 3 times 10, 5 times 6. And because this is negative, they are all negative. And the ones that add up to negative 11 are right there. So how does this look, the factored form? X minus 5 times x minus 6. Right, how about the next one? 9 and 6? Negative 9, negative 6, right? Again, 54 is one of those numbers that 9 times 6 ought to be like the pair you think of first. Now, if it's not right, there are some others, right? 54 could be 1 times 54, 2 times 27, 54, 3 times 18, 4, no, 5, no, 6 times 9 is the last one. I mean, if you start going down the list, right? 1 times 54, 2 times 27, all I did was I doubled this one and I cut this one in half. That has to work. Let's see, then we had the 3 times 18, right? That was like 3 times 1 is 3, so 54 divided by 3 is 18. And then we had the 6, so 4 didn't work, 5 didn't work, 6 works, and that's times 9. And you're done there, right? Because there'd be no numbers 7 and 8, they don't go in, and now you're at 9, and you already have a 9 in there, so you would be done. So this is the one. X minus 6, x minus 9. Oops. Okay, try this one. What are the first two numbers you think of when you see 40? I would think of 5 times 8 first, right? But then I would say, okay, 5 and 8 aren't going to work, and I would look a little harder. But I think 5 times 8 when I think 40. So, and what two numbers did you come up with? 10 and 4, right? So if it's -4 times -10, that gives us the positive 40. And then when you add them up, that gives you -14, right? So x minus 4, x minus 10. Okay. Now I imagine for a lot of you, you're looking at this saying, he said this is going to be hard. This isn't hard, but that's good. I hope it's not hard for you, really. Is anybody sweating? Okay. Okay. Quiet, please. Look it up. Look up here. So now, notice now that the last number is negative. So the two numbers are being multiplied together, and the result is negative. What does that tell you about the signs of those two numbers? One's got to be a positive, one's got to be a negative. Now, the middle term is negative. So which one is bigger, the negative or the positive? Basically, in absolute value terms, if you add them up and the result is negative, the negative is bigger than the positive, right? It has to be. So we need to think of the factors of 48. And 48 has a ton of factors, right? We have 1 times 48, 2 times 24, 3 times 16, 4 times 12, 5, 6 times 8. Okay, and because that's negative and that's negative, we know the bigger one of the two is negative. So which one of those add up to -2? 6 plus -8 is -2, right? So we're going to use these. X plus 6, x minus 8. Right? How about the next one? Again, it's the same pattern. Since the last term is negative, one's positive and one's negative. Since the middle term is negative, you know the bigger of those two is the negative one. So think of the factors of 15. 3 times 5. Okay, any way to, no? Try another one. Okay, 3 times 5 isn't going to work. What's the other? There's only one other possibility. 1 times 15, right? So if you had a 1 times 15, right, with the 15 being the bigger one, it's got to be the negative. 1 plus -15 or 1 minus 15, -14. X plus 1, x minus 15. So there's only one pattern that we haven't done yet, which is that. So that's negative and that's positive. We didn't do that. That's the only one we haven't done so far. Well, considering that A is 1, right, because we're not changing that at all. So we've already done positive, 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 negative. Now we've got negative, 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 positive is the next thing. Well, first you got to do this one. Do that one. Are we thinking of the factors? What's that? 6 plus negative 10 does not equal negative 7. Negative 12, positive 5, right? I mean, so this could be 1 times 60, 2 times 30, 3 times 20, 4 times 15, 5 times 12, what else? 6 times 10. And let's see, 7, 8, and 9, they're not going to work. The bigger one has to be negative. So which pair of numbers is it? 5 minus 12. So the answer is x plus 5, x minus 12. Right? Okay, now here's the promise. Last term is negative, middle term is positive. Okay, what did we learn from the fact that the last term is negative? That's that one's negative and one's positive. What did we learn from the fact the middle term is positive? The bigger one is positive, right? So when you add them up, you get a positive result. So let's think. 72, that's got a lot of factors. 3 times 24, 4 times 18, 6 times 12, 8 times 9. Okay, now, because that's a positive, we know the bigger number is positive and the smaller one is the negative. So which one of those add up to positive 6? The negative 6, positive 12. So x plus 6, no, x minus 6, x plus 12. Right. How about this one? Factors of 45, of negative 45, that add up to 4. Josh. When that's positive, right? Like we did in the last ones, when it was negative, then the smaller number was the positive. Okay. I can't hear you. Negative 5, positive 9. Okay? Good. Okay, if you can multiply, this is not hard. Try that one. What's that? What do you got? Negative 5, positive 10. Does that work? Negative 5, positive 10. No arguments. Everybody agrees. Negative 5, positive 10. If you multiply them, you get negative 50. If you add up, you get 5. X minus 5 times x plus 10. Okay. Now, there's some problems that are in there, which I'm going to show you how to do, and I included them in the homework. I didn't do them with my regular Algebra 2 class, and I'll show you why. But we'll see. This you could think of this as that situation where 8 is not equal 1, because 8 is not equal 1, right? It equals negative 1. But it's not dealt with in the same way as when a is any other number except for 1 and negative 1. It's like its own thing. And this is what they do to solve something like this. They say, let's write it like this. Make a set of parentheses, and then make each one of these the opposite sign. So this becomes x squared minus 14x minus 32. Right, so the minus in front of parentheses is if you distributed it, it would be negative x squared, positive 14x, positive 32. So they take a step so that what's inside the parentheses now is a positive 1. So now you can use the kind of thinking we've been doing up till now on this, right? What two numbers, their product is negative 32 and the sum is negative 14. 2, negative 16, right? So if I'm just dealing with this, I would say x plus 2, x minus 16, right? But then I have to deal with the minus in front. So then you stick the minus in front. So because of that minus that's there, it's a two-step process. First, factor out the negative. I say factor out, but think reverse distributive property. And then factor what's left inside the parentheses. Right. By putting a minus out in front of parentheses, it changes the sign of every term. Okay. Now, I find this a little odd, honestly, because remember why did I say we're learning how to factor? We're learning how to factor to solve equations, right? And if this were an equation, let's say I set this equal to 0, and I do not want to mess with this negative x squared. I want it to be positive x squared. What I would do in an equation is I would just multiply both sides by negative 1. And then that would turn this into positive x squared, negative 14x, negative 32. And what does it do to the right-hand side when I multiply? Nothing, right? So it's very painless to deal with this as an equation. You just multiply through by negative 1 and it's done. You would never do this, right? But there are times when we get to the chapter on rational functions where that is done sometimes, where they do factor out a negative. So it's not bad to do it. It's not hard, right? Try this one. Try this one here. Factor out the negative and then factor what's inside the parentheses and then stick a negative on it. Right. Right, so far. Good job. It's good. Get it, Gabby? Okay. Not hard, right? What'd you get? No, just leave it like that. Everything positive. Positive, positive. So that's plus 2, plus 4. Right? And then just, no, we're not factoring up there. We're factoring what's inside the parentheses here. What two numbers are product is 8 and the sum is 6. 2 and 4, like that. And then stick the negative in front. Okay, so take out a negative. See, yes?
Wouldn't they have to do like another set of parentheses around two groups for the negative sign?
No, it's making the whole thing negative, right? It's not. You don't need a negative on both. What would happen if you had a negative on both? It would be a positive. Then you'd have negative 1 times negative 1, which is positive 1. You definitely need just one negative sign that goes with this. Right? Negative x squared plus 6x plus 8. Right? And then that by itself is x plus 2 times x plus 4. And then you put the minus in front. Right? You're trying to stick another negative in here?
No, I mean add another parenthesis.
Well, you mean like this? Okay, that wouldn't accomplish anything. What you're thinking of is like if you had a distributive property, and that would be that you had a plus or a minus in there, like a subtraction, an addition, or a subtraction, but that's not what it is. These are all being multiplied together. It's three factors, -1 times x plus 2 times x plus 4. Okay, we're almost done. We're getting there, yeah. Isis, what you got? Would I do what? Can I put it in here? Sure. I mean, if you wanted to multiply that negative in here, make this -x minus 2 times x plus 4, you could do that. It's the same thing. Good question. Okay, that leads us to greatest common factor factoring. GCF. And thing about the GCF factoring is really important. It's like every time you're asked to factor something, the first thing you should look for is greatest common factor. You know, it's something that we use not just in this chapter on quadratics. In the next chapter on polynomials, you use it too. So for higher degrees, third degree, x to the third, x to the fourth, x to the fifth, you still look for greatest common factor. And you could think of it as like a reverse distributive property, right? In the distributive property, you have a number outside of parentheses, right? And an add or subtract inside. And you multiply both terms in the parentheses. 2 times x, 2 times 3. And you get that, right? In factoring, greatest common factor factoring, you look at those two terms and you try to imagine the distributive property that created that expression, right? You try to say to yourself, what would be the number outside parentheses that I could have used that would have created an expression of 4x minus 8? Now, you could look at it and say, well, how about 2? There's a 2 goes into both, and that would work, right? But it wouldn't be the greatest common factor. What's the greatest common factor between 4x and 8? 4. So, you know, you take that 4 outside parentheses, and what's left is whatever this is divided by 4, x, and whatever this is divided by 4, -2. Okay, you can always like show that what you've got is right by just do the distributive property on what you just did, right? 4 times x is 4x. 4 times -2 is -8. So yeah, that's good. Okay. So here's a couple examples, right? In this one here, there's two terms, right? Terms are separated by plus or minus, like additions or subtractions. What's the common factor, the greatest common factor in both of those terms? You know, if you're looking for the thing that's multiplying in that, if it helps, you could write it like 7n squared minus 7 times 3, right? So what's in common is the 7, right? So you take out 7 outside parentheses, and then what's left inside the parentheses? You know, what would you get if you divided 7n squared by 7? Just the n squared. What would it be left if you divided the 7 times 3 divided by 7? Just the 3. I mean, most of the time, you're not going to write a step like this. You're not going to write it like 7 times 3. You would just say, okay, 21 divided by 7 is 3. So that is greatest common factor factoring. Okay, what about this one? What does it look like, the common factor? Greatest common factor? 4, right? Is there a smaller common factor? Yeah, 2 would work. But 4 is the greatest common factor. So take it out in front of parentheses and then divide each term by 4. 4x squared divided by 4. Yeah, 8x divided by 4. And 12 divided by 4 is 3. Okay. Now, notice that what's in parentheses now is a simple quadratic trinomial. Is it factorable? Meaning, are there factors of 3 that add up to 2? No, there's not. So it's not factorable. So you're done. But you have to check. right? First you factor out the greatest common factor, and then you check to see whether what you've got left could be factored further. So this is not factorable, so you're done. Okay. So try that one. Greatest common factor factoring. I imagine it didn't take you too long to find the greatest common factor. What's that? So it's 9, right? So you take out the 9, x squared plus x minus 2. Okay, now you've got to ask yourself the question, is what's left in parentheses factorable?
Yes.
Are there factors of negative 2 that add up to positive 1?
Yes.
Well, what are the factors of negative 2? 1 times negative 2 or negative 1 times positive 2. Do either one of those add up to a positive 1? Yeah, negative 1 times 2. Right, so you could take this one more step, right? X plus 2, x minus 1. And you still got the 9. So always look for, if you could do any more factoring there. Just don't worry about the 9. Just look at this here. Are there factors of negative 2 that add up to 1? Remember, since that's negative, you know that one of the factors is positive and one is negative. Because that's positive, you know that the bigger of the two is the positive number. So that's plus 2 minus 1. Okay, and then there's one more. I don't really think they have any homework problems where this is actually going to be a problem, but it comes up, like I say, factoring is something that's just kind of embedded in everything we do from now on. And it will come up, right? And it's best shown by this example right here. What's the greatest common factor between those two? More. I mean, when you see the x squared, right, this means that x is a factor here twice. It's x times x. And this is here once, so what's in common in the two terms? Yeah, it's 2x is the greatest common factor. You got to take out the 2, and you got to take out the x. Okay, now, what's left when you factored the 2x from 4x squared? 2x, right? Which is 2x times 2x is 4x squared. That's good. What's left when you factor 2x from 2x? Okay, it's got to be minus 1, right? Don't think that because you took 2x outside parentheses that it leaves nothing, right? Because it's actually 2x divided by 2x, which is 1. And if you didn't put a 1 there, if you tried to do distributive property to get back here, you wouldn't be able to make two terms, right? You got to have that 1 right there. So we commonly forget that 1. Okay. Clear as mud, as I say? No, forget it. Go back to sleep. Okay. So we're like halfway through this stuff right now.